Episode 54, Voltage Dividers, the Handiest Ratio, Crash Course Instrumentation, Series Circuits and Amp, Voltage Dividers. 2 resistors, 1 beautiful ratio. That is the voltage divider. Quick roadmap, the 3 divider rules. We will prove and use. Rule 1, the ratio. Output voltage equals input voltage times the bottom resistance divided by the total resistance. Rule 2, unloaded only. The simple ratio assumes the output is not drawing current. Any load becomes part of the divider. Rule 3, output resistance matters. A divider behaves like a small ideal source in series with an output resistance equal to the top resistor in parallel with the bottom resistor. Hook wants 6 volts from 12 without a regulator? Put 2 equal resistors in series and take the output across the lower one. That is the divider in one sentence. Intuition first, picture a ladder of drops. In a series chain, resistances split the input according to their share of the total. If the bottom branch is half the total resistance, it gets half the voltage. If it is 1/3 of the total, it gets 1/3 of the voltage. Fast tie back to episode 53, same current everywhere in a series chain. Output voltage across the bottom resistor equals that same current times the bottom resistance. Swap in, current equals input voltage divided by total resistance, and you arrive at rule 1 in words. Walk through example. Speak the math. Build a divider with a 12-volt source, a top resistor of 6 kilo ohms, and a bottom resistor of 6 kilo ohms. Total resistance is 12 kilo ohms, so current is 12 volts divided by 12 kilo ohms, which is 1 milliamp. Output is the drop across the bottom resistor. 1 milliamp times 6 kilo ohms equals 6 volts. Half in, half out. Power check. Each resistor burns 6 volts times 1 milliamp, which is 6 milliwatts. Totals line up. Quick mental ratios you will use daily: equal resistors. Output is half the input. Bottom 1/4 of the total. Output is 1/4 of the input. Want 4 volts from 12? Make the bottom 1/3 of the total. Example, top 8 kilo ohms and bottom 4 kilo ohms. Rule 2 in the real world, loading changes everything. When you connect a device to the output, that device has its own resistance. It sits in parallel with the bottom resistor. The effective bottom resistance is now the parallel combination, which is smaller than before, so the output falls. Mini demo. Use 10 kilo ohms on top and 10 kilo ohms on bottom for a 6-volt output. Now add a load of 30 kilo ohms across the output. The effective bottom becomes 10 kilo ohms, in parallel with 30 kilo ohms, which is 7.5 kilo ohms. The new output is input times 7.5 divided by 10 plus 7.5, about 4.9 volts. That is the sag everyone sees. Rule 3. Treat a divider like a small source with a non-zero output resistance. Engineers often replace the 2-resistor ladder with a Thevenin model, an ideal source equal to the unloaded output voltage in series, with an output resistance equal to top in parallel with bottom. This makes load predictions fast and helps you choose values that will drive your circuit without big errors. Choosing resistor values that make sense. Large values waste less current, but raise output resistance and noise susceptibility. Good for high-impedance inputs like analog to digital converters. Small values drive loads better but waste more power as heat. Check wattage on higher voltage rails. Everyday choices often live between 1 kilo ohm and 100 kilo ohms. Start in the middle, then nudge up or down based on loading and power. Bench lab you can film in one take. Build a 12-volt divider with top 18 kilo ohms and bottom 9 kilo ohms. Predict output equals 12 times 9 divided by 27, which is 4 volts. Measure current. 12 volts divided by 27 kilo ohms is 0.44 milliamps. Add a load resistor equal to the Thevenin output resistance. Top in parallel with bottom. Watch the output drop to about half of the unloaded value. A textbook, Thevenin result, and a great visual. Fun history bite, Wheatstone's bridge. In the 1840s, we made ratio measurements the gold standard, long before digital meters. Dividers and bridges let engineers compare unknowns to precise known ratios. Late 19th century labs used slide wire potentiometers, essentially adjustable voltage dividers, to set and read exact voltages without drawing current from the device under test. That no-load principle is our Rule 2 in action. Safety and good practice. Do not power active electronics solely from a divider unless the load is tiny and constant. Use a regulator or reference for power rails. Put a small bleeder current through the divider so minor load changes do not swing the output wildly. A common starting point is a divider current that is 10 times the expected load current. For measurements, prefer inputs with very high resistance so they behave like no load. We will demo meter loading in a later episode. What is next? Episode 55 dives into potentiometers, the adjustable divider, plus best practices for set points and sensor scaling. We will also show tricks to buffer a divider so it does not sag. If this helped, tap like and subscribe so you catch the next episode. Drop a comment with your favorite divider values or a loading horror story.